Okay, thank you very much, Jonathan. Right. There we go. So if I had to choose my top 10 building conservation publications based on their usefulness and influence, I think that top of the list would definitely be this pamphlet, The Need for Old Buildings to Breathe, written by Philip Hughes and published by the SPAB in 1986. Funnily enough, 1986 was the year I started my building conservation career at South Somerset District Council. And over the following years, for me and my colleagues, this was really one of the go-to documents that helped explain some of the problems that we saw in old buildings and also helped frame our advice on how to repair them. And I'm pretty sure that all of you will be familiar with it. It stood the test of time, and in fact it was republished earlier this year with virtually no amendments other than some of the images and references. The basic text and advice remains the same, as well it should, because it's really good advice. But when we think about breathing, do we tend to think of a gas? After all, we breathe air, which is a gas. So is this property of breathability all about water in gas form? In other words, water vapour? Well, no, not really. And as the SPAB explains on its website, they use the term breathable to describe the extent to which building materials are able to transmit moisture. And the website goes on to explain the different mechanisms whereby materials do this. And of course, one way that water moves within a porous material is through vapour diffusion, through the pore network. And materials that allow water vapour to move through them are described as vapour permeable. But in reality, any pores just a little way below the surface of the material are not really affected to any large extent by outside conditions. So there's no real imperative for the vapour to move in any particular direction, and there's no directional flow of water vapour towards the surface. So what we call vapour diffusion is in fact a constant and very complex process of change between liquid and vapour phases, because pure vapour movement would be an incredibly slow process. Another mechanism is capillary flow, and this is the means by which liquid water moves through the network of pores in permeable materials. And this again is explained on the SPAB website. And there's also another mechanism at play, and that is hygroscopy. This is the ability of some building materials to absorb and hold moisture molecules in the internal surfaces of the pores during periods of high relative humidity, and then to release them as those humidity levels fall. Now, hygroscopy is important in buffering moisture, that is, regulating changes in indoor humidity without condensation forming on the walls. But in terms of movement of water through a building, we know that capillary flow, so that is the flow of liquid water, is by far the most effective and rapid mechanism. And at the conference session last week, my colleague Robin Pender explained in more detail why this is so. And if you weren't able to listen to the live event last week, I strongly recommend that you listen to the recording of her presentation, which is now available on the Historic England website. And I think Matt is going to put the link up there. Yeah, thank you. And it's really important to understand this because it's fundamental to our understanding of how buildings work, how to look after them, and how to dry them out when things go wrong. So just to sort of demonstrate the speed of capillary flow and the importance of capillary flow, we can look at the drying curves for a brick wall following flooding. This was part of laboratory tests carried out for us by Liz Laycock at Sheffield Hallam University a few years ago. And we can see that under normal drying conditions, there is an initial fairly rapid loss of water from within the brickwork, which occurs as liquid water is drawn through the material by capillary flow and evaporates from the surface. So that's represented by the steep part of the drying curve, and that is labelled stage 1 drying. And this shows that a lot of water, about 65% of the total in this case, is lost in a short space of time. And I like to think of this evaporation of liquid from the surface as perhaps more akin to sweating than breathing, hence the rather unglamorous title of my talk. But this drying stage is followed by a much slower phase called stage 2 drying, and that's where the remaining water, in this case about 35%, is dissipated. This is a much slower process, less than half the speed of stage 1, and this is because once the moisture content drops below a certain level, some of those liquid flow paths are broken, and with fewer liquid pathways, drying slows right down. So it's clear that movement of liquid water or capillary flow is much more effective at dissipating moisture than vapour diffusion, and in fact it's the only way of moving water through a porous material in really any meaningful way. So what about the role of lime mortar in dissipating and transmitting moisture from a building? So let's look at a cross-section of a masonry wall bedded and pointed in lime mortar. So water will enter the wall externally from rain, also from building defects, plumbing leaks and so on, and it may also be generated by the occupants or drawn up from groundwater. Water within the wall, once it's within the wall, it's drawn into the lime bedding mortar, and I'll come back in a moment later to explain quite why that is. But under drying conditions, depending on the permeability of the masonry units, some water may evaporate via the face of the stone or the brick, but most evaporates from the face of the mortar joint. So this means that any dissolved salts are deposited at or close to the surface of the mortar. And that's what this process can look like. So here you can see salts being deposited in the joints as water within those walls is being drawn through the mortar and evaporating. So this is the building sweating. So over time, this salt activity in the joints, perhaps combined with some dissolution of lime binder by acidic rainfall, results in the mortar gradually decaying. And this is what happens. So the mortar joints gradually recede, the masonry units remain in good condition, there's no drama, but eventually the wall may need repointing. And this is what we mean by sacrificial decay. The lime mortar deteriorates in preference to the masonry units. Now, a lot of you will be familiar with this process, and of course it's described and illustrated in the SPAB Need for Old Buildings to Breathe document. But have you ever wondered exactly why water in the wall is drawn into the bedding mortar in the first place? Well, we sometimes hear it said that it's because the mortar is more porous than the adjacent stone or brick. But that's only part of the story, because a material can have very high total porosity but be very poor at transmitting moisture if those pores are not well connected. So just think of something like pumice or expanded clay or foamed glass. Very porous, but they don't transmit water. So to transmit water, those pores need to be connected. So the materials need to be permeable as well. And as you can see from this thin section of a lime putty mortar, in which the voids are coloured blue, there's a high proportion of well-connected voids there. But critically, the pores in lime are the right size to permit capillary flow. Now, there is a range of pore sizes that allow capillary flow. Above a certain size, pores are too large, and below a certain size, they're too small. There's actually a bit of dispute amongst scientists about exactly where the precise limits are, but the lower limit is generally considered to be about 200 nanometers. So any pores in a porous and permeable material that are smaller than 200 nanometers are pretty much ineffective in terms of liquid water transport. Most traditional non-hydraulic lime mortars only have a small proportion of these very, very small pores. So the majority of their pores are actually capillary active. But that's not all. Critically, the majority of pores in a lime mortar are significantly smaller than the majority of pores in most porous building stones. So this graph here shows the distribution of pores of different sizes in a sample of sandstone and a sample of non-hydraulic mortar taken from a building. So the area beneath the curve or beneath the lines represents the total open porosity of the materials, and the height of the curves indicate the number of pores of a particular size. The purple line is the sandstone, And you can see that little red arrow there. The peak is around 15,000 nanometers. In other words, a large proportion of the pores of this stone are around that size. But if you look at the lime mortar, the main peak is only around 600 nanometers, and it's a broader peak, so most of the pores are above that critical 200 nanometer size and up to about 1100 nanometers. So both these materials, the lime and the stone, are both capillary active, but most of the pores in the mortar are much, much smaller than those in the stone. And when you put two capillary active materials with different pore sizes next to one another, the one with the smaller pores exerts strong suction on any water in the material with the larger pores and literally draws the water out of it. And of course, if that water contains dissolved salts, then they're carried along as well. And this is the same process that occurs when we use poultices to draw salts or contaminants out of stonework. And it explains why clay is such an effective poultice medium, because it's got much smaller pore size than the masonry to which it's applied. And it exerts that strong suction effect. But here you can see that suction effect playing out in those mortar joints as water and salts are carried through the mortar. Now, most non-hydraulic lime mortars have a high proportion of well-connected pores around the 1000 nanometer, or to put it more simply, 1 micron size. And this is very effective at transmitting moisture. And crucially, it's the carbonated lime binder that imparts this microstructure to lime mortar. And the more lime in the mix, the greater the potential benefit, which is why traditional lime-rich mortars were so good at doing this and have stood the test of time. There's a structural engineer called David Wiggins, and he's done a lot of work on this recently. He was commissioned by Historic Environment Scotland to produce a technical paper explaining this functional performance of lime mortars, and it's well worth a read. And I think Matt's got the link there and hopefully is going to paste that in there. Thank you, Matt. And also I must say thank you to David for permission to use his diagrams. So I hope that's explained in a little bit more detail, not only how lime mortars behave sacrificially and how they help dissipate moisture from buildings, but it's given you a better understanding of why they do that. So let's look now at what happens if an historic wall is repointed with mortar with low permeability. So this could be a cement mortar or even some natural hydraulic lime or NHL mortars, but one with either low total porosity and permeability, or one in which a considerable proportion of the porosity is below that critical 200 nanometer threshold and therefore not capillary active. So water enters the wall from all the usual sources, and it's drawn into the lime bedding mortar for the reasons that I've just explained, that strong suction. But evaporation from the surface is blocked by the impermeable repointing mortar. So the masonry adjacent to the mortar starts to wet up, and eventually water may start to evaporate from the edges of the masonry units, as there's just no other way for it to escape. So any soluble salts transported in the water are deposited in the stone or brick as that water evaporates. And this is what that process looks like. So the stonework on the left was repointed using an NHL mortar, which is nowhere near as effective at transmitting moisture as a non-hydraulic lime mortar. And this has resulted in salts accumulating in the stone blocks. And you can see the same thing happening in this brickwork, where a patch repair was carried out using cement mortar. Now, if the masonry material is very capillary active and evaporation is fairly slow and steady, then you probably won't see anything worse, at least in the short to medium term, than these sort of fluffy white salts appearing on the surface, and these can be brushed off from time to time. But if evaporation is more rapid, then the drying front will move behind the masonry surface, and salts crystallizing there are very damaging, and after some time the surface of the stone or brick powders away, and often leaving that cement mortar perfectly intact. And I'm sure you will have seen lots of examples of this, real sort of shop of horrors. The cement mortar determined to survive, usually till the bitter end, and no self-sacrifice going on there. So you could say that these walls are still sweating, but they're sweating from the wrong place. So we've looked at lime pointing, but what about lime render? Well, we found that this is even more effective than pointing at dissipating moisture because it extends that poulticing effect over the entire face of the wall and it actively dries it. So lime render with a concentration of pores around the 1 micron mark is more capillary active than the stone or brick that it is applied to. So it doesn't just allow water to evaporate from the surface, but it actively pulls it towards the surface. And in our damp towers research, which Nikki is going to talk about later, we found that renders both help to prevent wetting, but also promoted drying. And to continue the sweating analogy, you could say that it acts in a similar way to a wicking layer in outdoor clothing. So it transports sweat away from the body and allows it to evaporate, leaving the wearer dry and comfortable. And what about lime wash? This can be applied either direct to flush pointed masonry or to lime render and plaster. And you probably all know that one of the benefits of lime wash is that it doesn't impede moisture transfer, so it allows water from within the wall to escape. But research carried out in Portugal a couple of years ago showed that not only did lime wash not hinder the drying of various stone and lime mortar substrates, but it actually enhanced drying, and that the wetter the substrate, the greater the benefit. And at high moisture contents, the drying rate of lime wash samples was around 50% more than the non-lime wash samples. Yeah, and Matt's put the link up there to that, the paper that describes that research. And that begins to make some sense when we think about this microstructure of lime that I described a minute ago. The lime wash has a higher concentration of capillary active pores than the substrate, so it's exerting that poulticing effect, even though it's a very thin layer, and it's actively drying the substrate. So far I've concentrated on external finishes, but what about internal plaster? A few years ago, my colleagues Ian McCaig and Brian Ridout were involved in developing our guidance on flood recovery in traditional buildings. And in visiting various sites and discussing remedial work, it became clear that historic lime plaster was often being stripped out of buildings after flooding because there was a feeling that it was holding moisture in the wall and slowing down the drying. So Ian and Brian did some small-scale experiments to look at this, but found no evidence that the plaster was slowing the drying rate. And again, there's a link to that research report in the chat. And I think it might be useful to test this further in a larger scale experiment or some site trials. But if we look at the pore size distribution of a typical historic lime plaster, this one is from a building in Somerset, we can see that it's got a very high concentration of these capillary active pores around the 1 micron mark. So my guess would be that the lime plaster would work in much the same way as an external render and actively dry the wall. We also know that lime plaster is a hygroscopic material, so it certainly plays a major role in moisture buffering and regulating variations in internal humidity. So that alone really is reason enough to use it. So just to recap, lime mortar, render, plaster and lime wash not only protect buildings from water penetration, but because of their properties of porosity, permeability and capillarity, they exert this poulticing effect on the walls to which they're applied, and they promote active drying and dissipation of moisture from masonry. And as we know, a dry wall is warmer, so it will take less energy to keep the occupants comfortable, and there will be less risk of frost damage of saturated masonry. Now, clearly, impermeable renders, plasters and paints don't allow water through at all, and you'll all be familiar with the sorts of problems that happen when they're used on old buildings, so I'm not going to dwell on that. But let's look instead at so-called breathable products. Now, there's a wide range of proprietary paints, coatings, plasters and renders marketed as breathable, and yeah, breathability is one of their biggest selling points. But when you look closely at the details, you can see that most of the manufacturers of these products equate breathability solely with vapor permeability. And a large number of them actually say that the products have high vapor permeability and low capillarity, as if that is a good thing. But is that what we want for our buildings? So remember that the SPAB definition of breathable includes capillary flow of water. And we know, and I hope I've just demonstrated, that this is the main way in which a masonry wall transports moisture. So if we use that wider SPAB definition, these so-called breathable products are not, in fact, very breathable at all. My colleague Ian McCaig used his time in lockdown earlier in the year to do an initial small-scale experiment on the effect of a vapor-permeable water-repellent coating on the drying rate of saturated brick. So he used these little prisms of clay brick from a late 18th century building. One sample was treated on the face with a well-known colourless water-repellent treatment, and the other was left untreated. The samples were weighed, soaked in water until they were saturated, and then the weight recorded again. Now, it was clear that the water repellent had penetrated about 5 millimeters into the face of the brick, and you can see this in the lighter coloured hydrophobic zone in the image on the left, and this did not wet up appreciably when the brick was soaked in water. So once they were wet, the backs and sides of both samples were then sealed with impermeable film and tape, as shown in the right-hand picture, so that evaporation could only take place through the face. And then they were allowed to dry in ambient conditions, approximately 21 degrees and 65% relative humidity. And they were both weighed at regular intervals until they reached a constant weight and had effectively finished drying. So the drying curve for the untreated sample, shown by the orange dots, follows that typical two-stage drying of porous materials which I explained earlier. So the initial first stage drying is relatively rapid as water moves in liquid form towards the surface where it evaporates. That's shown by the steeper part of the curve, up to about 3,000 minutes or just over 2 days. The second stage drying is slower as the number of liquid pathways are reduced. But the sample was air dry after about 5,000 minutes or almost 3.5 days. The drying curve for the treated sample is shown by the blue line. The difference in initial moisture content between the two saturated samples is due to that hydrophobic zone which I mentioned earlier, which did not absorb any water. So the drying curve shows a more or less uniform rate of drying, which is much slower than the first stage drying of the untreated sample. And the gradient of the curve is similar to the second stage drying. So this suggests that the water repellent treatment eliminates first stage drying because it significantly reduces the liquid pathways through that hydrophobic zone. And with fewer liquid pathways, the drying process is much more akin to stage 2 drying, and as I explained earlier, that is very slow. So in this experiment, it took 13,000 minutes, or just over 9 days, for the treated sample to dry. And this was 2.6 times longer than the untreated sample. Now, these are not particularly large samples, but imagine how much longer it would take for moisture from deep within an entire wall to dry out through one of these coatings. There's a risk that it would just never make it before some new source of moisture ingress into the wall topped up the moisture lost by this slow drying process. And indeed, there's a great risk that the wall would become progressively wetter. So the idea of coating your building with something that has low capillarity, even if it has high vapor permeability, only makes sense if the only moisture entering the wall is rain. But we know that moisture is also generated from within a building, enters the wall via defects in the building envelope or from plumbing leaks, and is drawn up from the ground, especially where there is poor ground drainage or leaks in a water main or sewer. So we need materials that will not so much stop rain getting into a wall as actively encourage moisture from all sources to evaporate from the wall surface. And I hope I've demonstrated that traditional lime mortars, renders, plasters and lime wash are the perfect materials to do this. They're breathable according to all the criteria of the SPAB definition. As well as dissipating moisture, they decay sacrificially. They have a long track record of success. They look fantastic. So what more do you want? Thank you.